Introduction. Today, two friends, Roy and Sid, came on a beachside for picnic and they both are enjoying very well. This beach is full of nature and I like this kind of landscape so much. Roy, see the high sea waves there, looking so glorious, don't you think? Yeah, it's amazing. But do you know, these sea waves follow which phenomenon? No, can you please tell me? Yeah, sure. These sea waves follow oscillations. They repeat their motion periodically. Okay, I got it. I want to know more about it. Can you tell me? Of course I will. Students, in this lesson, we will learn about oscillations. Objectives. At the end of this lesson, you will be able to define oscillation and terminologies, understand simple harmonic motion, analyze simple harmonic motion with uniform circular motion, calculate velocity and acceleration in simple harmonic motion, define force law for simple harmonic motion, calculate energy in simple harmonic motion, analyze oscillations due to a spring, know about simple pendulum, understand damped simple harmonic motion, define forced oscillations and resonance. Periodic and oscillatory motions. Periodic motion. It is that motion which repeats itself after equal intervals of time. The interval of time is called the time period of periodic motion. Some examples are motions of planets around the sun, rotation of Earth about its polar axis, motion of the hands of a clock. Oscillatory motion. If a body moves back and forth repeatedly about a mean position, it is said to possess oscillatory motion. Some examples are motion of the pendulum or a wall clock, oscillation of a mass suspended from a spring, motion of swing. Period, frequency and displacement. Period. The smallest interval of time after which the motion is repeated is called its period. Period is denoted by the symbol T. Its SI unit is second. Frequency. The number of cycles completed in 1 second is called the frequency of oscillation. The reciprocal of T gives the number of repetitions that occur per unit time. It is represented by the symbol V. The relation between V and T is V is equal to 1 by T. The unit of V is per second and is called Hertz. Displacement is defined as the change with time of any physical property under consideration. Let's take an example. A block attached to a spring, the other end of which is fixed to a rigid wall. The block moves on frictionless surface. The motion of the block can be described in terms of displacement x from the wall. Simple harmonic motion. Simple harmonic motion is a periodic to and fro motion in a straight line about a mean position in which acceleration is proportional to displacement and is always directed towards the mean position. Consider a particle oscillating back and forth about the origin of an x-axis between the limits plus a and minus a. It is simple harmonic motion if the displacement x of the particle from the origin varies with the time as xt is equal to a cos omega t plus phi, where a is equal to amplitude, omega is equal to angular frequency, phi is equal to phase constant. In simple harmonic motion, displacement is a sinusoidal function of time. Simple harmonic motion and uniform circular motion. The projection of uniform circular motion on a diameter of the circle follows simple harmonic motion. Let us take an example for better analysis. Tie a ball to the end of a string and make it move in a horizontal plane about a fixed point with a constant angular speed. The ball would then perform a uniform circular motion in the horizontal plane. Observe the ball sideways or from the front. Fixing your attention in the plane of motion, the ball will appear to execute to and fro motion along a horizontal line with the point of rotation as the midpoint. You could alternatively observe the shadow of the ball on a wall, which is perpendicular to the plane of the circle. In this process, what are we observing is the motion of the ball on a diameter of the circle normal to the direction of viewing. Velocity and acceleration in simple harmonic motion. The speed of a particle v in uniform circular motion is its angular speed omega times the radius of the circle A. V is equal to omega A. The direction of velocity v at time t is along the tangent to the circle at the point where the particle is located at that instant. The velocity of projection particle is given by Vt is equal to minus omega A sine omega t plus phi, where negative sign shows that Vt has a direction opposite to the positive direction of x-axis. Instantaneous acceleration of a particle undergoing simple harmonic motion can be determined by the method of reference circle. The centripetal acceleration of a particle p in uniform circular motion has a magnitude of v square by a or omega square a, and it is directed towards the center, that is, the direction is along PO. The instantaneous acceleration of the projection particle p dash is given by at is equal to minus omega square a cos omega t plus phi is equal to minus omega square xt. Example. Let us take an example of velocity and acceleration in simple harmonic motion. For a simple harmonic motion with amplitude 3 cm and time period 5 seconds, find the velocity and acceleration at equilibrium position and displacement of 2 cm from equilibrium position. Let us see the solution. Here, amplitude A is equal to 3 cm and angular frequency omega is equal to 2 pi upon t is equal to 2 pi upon 5 radian per second. The expressions for velocity and acceleration in terms of displacement are v is equal to omega under root of a square minus y square and a is equal to omega square y. At midpoint y is equal to 0. Hence, v is equal to omega a is equal to 3.77 cm per second and a is equal to 0. At y is equal to 2 cm we get v is equal to 2 pi under root 5 upon 5 is equal to 2.81 cm per second. A is equal to omega square y is equal to 2 pi upon 5 whole square into 2 is equal to 3.16 cm per second square. Force law for simple harmonic motion. To calculate the force acting on a particle of mass m in simple harmonic motion, we are using Newton's second law of motion and the expression for acceleration of a particle undergoing simple harmonic motion. Ft is equal to ma. Putting value of a, we get Ft is equal to minus m omega square x of t. Ft is equal to minus k x of t. Here, k is equal to m omega square. Omega is equal to under root k upon m. Force is always directed towards the mean position. Hence, it is sometimes called the restoring force in simple harmonic motion. The force is linearly proportional to xt. A particle oscillating under such a force is called linear harmonic oscillator. Energy in simple harmonic motion. Kinetic energy. Velocity of a particle executing simple harmonic motion is a periodic function of time. It is 0 at the extreme positions of displacement. Kinetic energy is given by k is equal to half mv square is equal to half m omega square a square sine square omega t plus phi is equal to half ka square sine square omega t plus phi. It is also a periodic function of time, being 0 when the displacement is maximum and maximum when the particle is at the mean position. Potential energy. The spring force F is equal to minus kx is a conservative force with associated potential energy. U is equal to half kx square. Hence, the potential energy of a particle executing simple harmonic motion is ux is equal to half kx square is equal to half Ka square cos square omega t plus phi. Thus, the potential energy of a particle executing simple harmonic motion is also periodic, with period t by 2 being 0 at the mean position and maximum at the extreme displacements. Total energy. Total energy of the system is E is equal to U plus K is equal to half K A square sin square omega t plus phi plus half K A square cos square omega t plus phi is equal to half K A square. Hence, the total mechanical energy of a harmonic oscillator is independent of time. Oscillations due to a spring. A linear simple harmonic oscillator consisting of a block of mass m attached to a spring. The block moves over a frictionless surface. The box, when pulled or pushed and released, executes simple harmonic motion. Hooke's law states that a system, when deformed, is subject to a restoring force, the magnitude of which is proportional to the deformation or the displacement and acts in opposite direction. At any time t, if the displacement of the block from its mean position is x, the restoring force F acting on the block is Fx is equal to minus Kx. Here, K is the spring constant. A stiff spring has large value of K and soft spring has small value of K. For this system, angular frequency is given by omega is equal to under root K upon m. And time period of the oscillator is given by t is equal to 2 under root m upon k. Simple pendulum. A simple pendulum can be made by a small bob of mass m tied to an inextensible massless string of length L. The other end of the string is fixed to a support in the ceiling. The bob oscillates in a plane about the vertical line through the support. This periodic motion is simple harmonic for small displacements from the mean position. Theta is the angle made by the string with the vertical. When the bob is at the mean position, theta is equal to 0. There are only two forces acting on the bob given by the tension T along the string, the vertical force due to gravity. The force mg can be resolved into the component mg cos theta along the string and mg sin theta perpendicular to it. Torque tau about the support is entirely provided by the tangential component of force given by theta is equal to minus L mg sin theta. For the system, angular frequency is given by omega is equal to under root mgl upon I. And time period is given by t is equal to under root I upon mgl. Since the string of the simple pendulum is massless, the moment of inertia I is simply ml square. Now, time period of a simple pendulum is t is equal to under root L by g. Damped simple harmonic motion. Sometimes the motion of a simple pendulum swinging in the air slows down and down. This is because the air drags and the friction at the support opposes the motion of the pendulum and dissipates its energy gradually. These are called damped oscillations. In damped oscillation, the energy of the system is dissipated continuously, but for small damping, the oscillations remain approximately periodic. The dissipating forces are generally the frictional forces. The damping force depends on the nature of the surrounding medium. If the block is immersed in a liquid, the magnitude of damping will be much greater and the dissipation of energy will be much faster. The damping force is generally proportional to velocity of the bob and acts opposite to the direction of velocity. If the damping force is denoted by Fd, we have Fd is equal to minus Bv. Forced oscillations. When a simple pendulum is released, it oscillates with its natural frequency omega, and the oscillations are called free oscillations. All free oscillations eventually die out because of the ever-present damping forces. When an external force maintains the oscillations, then these are called force or driven oscillations. The external force is itself periodic with the frequency omega d, called the driven frequency. The system oscillates not with its natural frequency omega, but at the frequency omega d of the external force. Resonance. The phenomenon of increase in amplitude when the driving force is close to the natural frequency of the oscillator is called resonance. Let us understand with an example. 5 simple pendulums of different lengths are suspended from a common rope. The pendulums 1 and 4 have the same lengths and the others have different lengths. Now, let us set pendulum 1 into motion. The energy from this pendulum gets transferred to other pendulums through the connecting rope and they start oscillating. The driving force is provided through the connecting rope. The frequency of this force is the frequency with which pendulum 1 oscillates. The response of pendulums 2, 3 and 5 are: they first start oscillating with their natural frequencies of oscillations and different amplitudes, but this motion is gradually damped and not sustained. The response of pendulum 4 is in contrast to this set of pendulums. It oscillates with the same frequency as that of pendulum 1 and its amplitude gradually picks up and becomes very large. A resonance-like response is seen. Assessment. Before proceeding further, let us know how much have you learned. Drag and drop the correct option. Did you know? The potential energy is minimum at midpoint of motion and at maximum displacement, the potential energy is maximum. The rise and fall in sea level is because of tidal forces and the tidal current that is created is an oscillating moment. In 1656, the Dutch scientist Christian Huygens built the first pendulum clock. This was great improvement over existing mechanical clocks. Their best accuracy was increased from around 15 minutes deviation a day to around 15 seconds a day. Summary. Let us summarize what we have learned. The motion which repeats itself after equal intervals of time is called the periodic motion. If a body moves back and forth repeatedly about a mean position, it is said to possess oscillatory motion. The number of cycles completed in 1 second is called the frequency of oscillation. The change with time of any physical property under consideration is called displacement. Simple harmonic motion is a periodic to and fro motion in a straight line about a mean position in which acceleration is proportional to displacement and is always directed towards the mean position. The total mechanical energy of a harmonic oscillator is independent of time. When a simple pendulum is released, it oscillates with its natural frequency omega, and the oscillations are called free oscillations. The phenomenon of increase in amplitude when the driving force is close to the natural frequency of the oscillator is called resonance.